Welcome to this deep dive. Our mission today is to cut straight to the technological core of modern artificial intelligence.
Yeah, we're talking about the fundamental architecture that powers basically everything you use. ChatGPT, Claude, Gemini, you name it.
They all rely on one single foundational idea, the transformer.
And look, if you want a shortcut to being genuinely well-informed about AI, you have to understand where the transformer came from. It feels like this overnight success, right? The famous 2017 paper, Attention is All You Need, just lands and changes everything.
But it's not the whole story.
Not at all. The truth is that breakthrough was only possible because, a whole generation of researchers had spent decades solving three really fundamental problems first.
That's right. And we've got a detailed stack of sources here that maps out that exact evolution. So today, we're going to trace that lineage for you. We'll show you how researchers systematically knocked down three huge hurdles in sequence modeling.
First, there was the vanishing context problem, then the single fixed-length bottleneck.
And finally, the crippling linear speed constraint.
And we want to keep this discussion clear, but also, detailed. We know you appreciate not just the what, but the why behind these massive shifts.
So as we unpack these three leaps, maybe keep a question in the back of your mind. Which one of these fixes do you think was the single most critical step toward the AI we have today?
That's a great question to hold on to.
Okay, so let's jump in. To understand the first breakthrough, we have to go back to why early AI was just terrible at language.
The core issue is that language is sequential. It's all about order. The meaning of a word, especially something like a pronoun, it, depends entirely on what came before, sometimes sentences before.
Right, and simple feed-forward networks, they just couldn't handle that.
No, they processed every word in total isolation. They had zero memory. By the time the network saw the end of a sentence, it had already forgotten the beginning.
So the first real attempt to solve this memory problem was the recurrent neural network, the RNN.
Exactly. Conceptually, RNNs were brilliant. They introduced a loop. The network would, process the inputs one by one, and at each step, it would take the output from the previous step and feed it back in.
So it was the first real attempt at modeling a sequence, or time.
It was. If your sentence had, say, 10 words, you had 10 sequential processing steps, each one informing the next.
That sounds like it should have worked. I mean, that sounds like it solved the context problem right there.
It should have, but it created a new problem, a failure mode that honestly crippled the field for years, the vanishing gradient problem.
Okay, break that down for us.
So during training, the network learns by adjusting its parameters. It does this based on a teaching signal, the gradient, that flows backward through the network.
Right.
With an RNN, that signal had to flow backward through time, through all 10 of those sequential steps, all those matrix multiplications. And with each step back, the signal got multiplied by a small number, and it just faded. It shrank towards zero.
Ah, so it's like a massive game of telephone. The message just gets weaker and weaker the further back it has to travel.
That's a perfect analogy. By the time that learning signal got back to the weights that processed the first few words of a long sentence, there was nothing left. The network literally couldn't learn from them.
So it could remember the last few words, but the deep context from the beginning was totally lost.
Completely lost. And this was immensely frustrating. It wasn't until the mid-90s that two researchers, Hochreiter and Schmidhuber, proposed the solution. The long short-term memory network, the LSTM. This was the first great breakthrough.
What was the big idea behind the LSTM? How did it solve that vanishing signal?
The mechanism was the clever part. LSTMs are a type of RNN, but they have these things called gates inside them.
Kate?
Yeah, they're like little internal neural networks that learn what information to keep, what to update, and crucially, what to forget. It's like a regulated conveyor belt for information. It could decide to protect the important gradient signal and let it pass all the way back unfaded.
Okay, so the gates made sure the important parts of the message in that game of telephone were preserved.
Precisely. It allowed the network to finally learn these long-range dependencies.
But the sources say LSTMs were invented in the 90s, but they didn't really dominate NLP until, the early 2010s? Why the long wait?
They were just too expensive, computationally, I mean. The concept was sound, but the hardware and the data sets we had back then, we just couldn't train them at any real scale. They were too slow.
And then GPUs came along?
And then GPUs, better optimization techniques, and huge new data needs all came along in the early 2010s. Suddenly, LSTMs were practical, and once they were, they just took over. They solved that vanishing context problem and really started the first golden age of neural language processing.
Okay, so memory is solved. But even with LSTMs remembering long sequences, the field hit a second completely different wall.
Yep. Specifically in sequence-to-sequence tasks. Think machine translation. This is what we call the single fixed-length bottleneck.
Explain that. What was the setup?
Imagine you're translating a sentence. The standard model had two parts. An encoder LSTM, which would read the entire input sentence, say, in English.
And its job was to...
What? Its job was to compress the meaning of that entire sentence into a single fixed-size vector. Just a list of a few hundred numbers.
Wait, the whole sentence?
The whole sentence. And that single vector was the only thing. The second part, the decoder LSTM, could see when it started generating the translation word by word.
That seems obviously flawed. It's like summarizing a complex novel on a single sticky note and then asking someone to rewrite the entire book from just that note.
You're guaranteed to lose everything important. It was a massive information choke point. It couldn't capture nuance or the meaning of a long, complicated sentence, and the performance just tanked as sentences got longer.
I can imagine. It also couldn't handle different grammatical structures between languages, right?
No chance. The summary just wasn't rich enough. The memory was fixed with LSTMs, but the way of transferring that memory was fundamentally broken.
So what was the conceptual leap that broke this bottleneck?
The key insight was realizing the decoder shouldn't have to rely on just that one static summary. Why not let it look back at everything the encoder saw along the way?
Ah, so give it access to the intermediate steps.
Exactly. And that was breakthrough number 2, attention. Introduced in 2014 by Bottleneck, Cho, and Bengio.
How did the attention mechanism actually work?
So the encoder still processed the input sentence, but instead of throwing away all the intermediate hidden states, it passed all of them to the decoder. And the attention mechanism, at every single step of generating the output, allowed the decoder to look back and decide which of the input words were most important for the word it was about to generate.
Okay, so if the decoder is about to output the German word for cat, it learns to pay high attention to the English word cat in the input, and mostly ignore everything else for that specific step.
Precisely. It created this dynamic alignment between the input and the output. It was transformative. These attention-based models didn't just beat the older bottleneck models, they demolished them. They even started outperforming the mature production-grade statistical systems that companies like Google were using.
I remember that. That's when online translation suddenly started to feel usable, not just a word-for-word swap.
That was attention solving the alignment problem. But we still had one final constraint. A speed barrier that was preventing the massive scaling we see today.
Okay, so we've solved memory with LSTMs, we've solved alignment with attention. What was left?
Recurrence. The LSTMs themselves. They were still, at their core, sequential. To process word B, you had to wait for the entire computation for word A to finish. They were chained together one at a time.
Which means your training time scaled linearly with the length of the sentence. If you want to double the context, you double the time.
Exactly. And when researchers realized that truly general AI would require training on, billions or even trillions of words, that linear scaling became an impossible bottleneck. It was just too slow, too expensive.
And that leads us straight to 2017. Breakthrough 3. The transformer.
Yes. And this was so radical because it questioned the most fundamental assumption everyone had been working with, the idea that you even needed recurrence.
The attention is all you need, paper.
Right. The authors realized they could scrap recurrence entirely, just get rid of the LSTMs and build the whole thing out of a new kind of attention mechanism they called self-attention.
But wait, if they got rid of the R and N part, how did the network know the order of the words? How did it maintain any context?
This is the elegant part. Instead of processing sequentially, the transformer creates a representation and embedding for every single token in the input sequence all at once. And then self-attention allows every single token to look at every other token in the sequence simultaneously to figure out how they relate to each other.
So instead of going A, then B, then C, it processes A, B, C, D, and E all at the same time, in parallel.
That's the key. By processing the entire sequence in parallel, it perfectly leveraged modern hardware. GPUs are designed for this kind of parallel matrix math. The linear time constraint just vanished.
So it wasn't just a technical upgrade, it was an economic one. It made hyperscaling financially possible.
Absolutely. The transformer architecture mapped the problem of language onto the hardware we already had. And the crazy thing was, it wasn't just faster, it was also slightly more accurate on translation benchmarks.
Speed and accuracy. The debate was over.
The debate was over. The transformer was the new foundation.
And from there, the innovation shifted from the core mechanism to how you configure it, right? The original
Yeah.
paper had an encoder and a decoder.
Exactly. And pretty quickly, researchers started specializing. You got encoder-only models like BERT, which are fantastic at understanding text, think search engines. And critically, you got decoder-only models like the GPT series, which are purely focused on predicting the next word in a sequence.
And it's that decoder-only next word prediction model that, when scaled up, gave us the large language models we have today.
This scalability led to the biggest paradigm shift of all. Before, you build a special model for translation, another for summarization. But when you train these decoder-only transformers on just insane amounts of data, they start to exhibit general behavior.
To start looking less like specialized tools and more like general problem solvers.
Right, and that's where the idea of prompting comes from. We didn't have that before. You didn't just chat with a translation model. The scaling of these transformer variations created the generally intelligent, interactive systems we know today, where you can just ask it to do almost anything.
So if you connect all the dots, this whole history shows that the path to today's AI was really about systematically identifying and then smashing these fundamental computational roadblocks.
One after another. LSTMs fixed the memory problem. Attention fixed the single vector information bottleneck.
And the transformer's self-attention fixed the sequential speed limit. Each one was a necessary step for the next. So what does this all mean for you? The AI tools you use every day are the direct result of researchers overcoming those three specific architectural hurdles. It's a clear roadmap of innovation.
And I think the big lesson from this journey is that huge breakthroughs often come from challenging the most basic assumptions you have, like the idea that you need to process language sequentially. That revolution is here, but the sources seem to imply the next big challenge isn't a new architecture, but rather the engineering and infrastructure needed to sustain this incredible scale.
We really hope this breakdown helped you get your head around the backbone of modern AI, and we would genuinely love to hear your thoughts. Which of these three developments, LSTMs, the general concept of attention or the leap to parallel self-attention, do you think was the single most profound leap for AI?
Let us know in the comments. We read all of them, and it really helps us figure out what to cover next.
If you enjoyed this deep dive, please show your support by liking this discussion, subscribing to the channel for more, and sharing it with anyone else who loves to learn. And don't forget to hit that notification bell so you get our new deep dives delivered straight to you.